First, let me thank the organizers for inviting me here to this interesting program at the institute. This is actually my first time visiting to India. So let me tell you a very simple, embarrassingly simple story, and in some sense, the work still in progress, done by my undergraduate student Gao Zhichang and my graduate student Yang Hui in Peking University. Hopefully, I have already figured out all of the mistakes they have made. And if not, if you can point out some problems, also I would be very grateful. So I think Ashwin already gave some introduction about this twisted bilayer graphene last week, but let me just still quickly give you this background. So we have this so-called magic angle twisted bilayer graphene, theoretically proposed by McDonough, actually also by some earlier theorists, that when you stack these graphenes together but twist the two layers a little bit, you form these Moiré patterns, and the band structure has this feature that if you tune the twist angle, and that changes this ratio between the interlayer coupling to this energy splitting in some sense between the Dirac points, then you can somehow make the Fermi velocity at the Dirac points to be 0. And actually, not only the Fermi velocity becomes 0, the entire Moiré band becomes somewhat flat. So this is the original from this original paper, McDonough's work, that at this 1.05 degree twist angle, this Moiré band becomes really flat. And actually, there's other magic angles, a sequence of magic angles. Other magic angles, I don't think they have a very simple interpretation though. And the real breakthrough happened in 2018 that the Pablo MIT group really made these materials, made good samples of the twisted bilayer graphene. I mean, in previous years, I think some other group, experimental group, may have accidentally made this sample, but the quality is not that good. And the Pablo group really, figured out, for example, this magic angle, which is roughly consistent with McDonough's prediction. And they also give this very nice picture, simple explanation why that this Moiré band becomes rather flat. You just because of the twist, there was two Dirac cones of the two layers are spatially separated in momentum space, and you mix this bands by this interlayer coupling by this trans W, and if this trans W and this interlayer energy spacing are comparable, then you have a rather flat band. And most interestingly, that with this flat band, you certainly expect very interesting physics, and they actually observe some so-called correlated insulator at so-called half filling. So this half filling originally could be very confusing. So previously in graphene, we thought half filling is talking to this charge neutrality Dirac point, but here by half filling they actually mean this on top of this charge neutrality point, which is labeled as n equal to 0, you'll still have half electrons per spin and per valley. That is this plus or minus 1/2, n equal to 1/2. And they found, well, this n equal to plus minus 1 should be trivial band insulator, but this n equal to plus minus 1/2, they still found the insulating behavior. This is conductance. And this is probably due to strong correlation from this flat band. And also, this insulator can be killed by small magnetic field. And they suggest this is some spin singlet mount-like insulator. And moreover, the same group actually published the same year, same issue of Nature, the reported superconductivity in this twisted bilayer graphene. And adjacent to this insulating half field, so-called half field insulating phases, you have this dome of simulator, and with TC about 1 Kelvin, not very high, but not too bad. And also small magnetic field around 1 Tesla can suppress superconductivity, both in plane and out of plane direction. And moreover, they also observed superconducting oscillation. And for this superconducting dome, I think it's very too small for you to see probably here. And for this region, this superconducting oscillation indicates that you have a rather small Fermi surface. So if you compare the ratio between superconducting gap and TC versus Fermi energy, then it's a very large ratio, actually comparable to unconventional simulators like cupids. So they claim this is indication that you have unconventional simulator. fine. All of these are, of course, very exciting. And later, I mean, this field really exploded, and people did a lot of other interesting experiments. For example, they observed anomalous Hall effect, which is whatever Gaussian group, but this is this anomalous Hall effect hysteresis. And the same to indicate also you have spontaneous ferromagnetism. And also they can tune the magic angle by pressure, so basically tuning this interlayer coupling. This is a correlated group. Also, they have similar materials. You don't have to twist. You can make a tri-layer graphene on top of a boron nitride that naturally form a Murray lattice. This is done by Fa Wang's group in Berkeley. And also, nowadays, people twist all kinds of two-dimensional materials and make Murray bands. And so, as a theorist, what we can do? So I realized I cannot really do anything more. But people already made a lot of theories for all this insulator or supernator. So I'm listing, of course, the incomplete list of existing theories. I mean, I apologize if somehow your theory has been omitted here. So this is Asher and Santil's work that they propose. This is insulator, so-called valley-ordered multi-insulator. I still have to figure out the real exact meaning of that. And I think this is Subhro's idea that this may be a spin-dense wave with 120-degree like magnetic order, anti-magnetic order. And for the simulator, people also made various predictions. This is McDonald's group and Bernie's group. They propose, okay, maybe it has a simple electrophonon, simple S-wave simulator, and more exotic states like, for example, Chenke and Valence. And some of my friends in China propose this is a D plus ID Carol simulator. And Liang Fu proposed this also as a dense wave insulator and maybe DL peak wave simulator. And even some group in China, Fu Chun Zhang's group, proposed this maybe even F wave simulator. So as you can see, as a theorist, I mean, I originally tried to avoid this field, but nowadays, I mean, people have to do it. When I entered this field, I realized I cannot do any new theory anymore because everything has been predicted. So what can I do? Well, my idea, as an undergraduate student, I was actually an experimentalist, so I always think about experiments. So my idea is very simple. I just try to see if I can propose some simple experimental probe to detect all these proposed superconducting pairing symmetry. And I searched the literature, and surprisingly, not many people tried to do this. I think this is probably only one I found by Sankata-sama, that they propose you can apply implant magnetic field, rotate the implant magnetic field, and also apply implant strain and see how this TC respond to that. And that way you can distinguish some of this proposed unconventional superconductor. And my idea is very simple. I mean, we did this also for ionic tests some time ago. But you just look at, I mean, the impurities, defects in the material. Of course, there must be naturally existing defects. For example, in graphene, we have a carbon vacancy. And also, you can artificially put impurities, like add atoms, onto graphene and see what's the effect of this on superconductivity. And that's a very simple idea. So, I mean, as a background, the impurities graphene has some interesting feature. Actually, one of the previous speaker already talked about this already. So if you look at one of carbon vacancy in graphene, that will induce, react fermions that will induce a energy zero quasi-bound state. I mean, the wave function is 1 over distance, not truly localized. Also, I mean, this is not only a theoretical question. So actually, in practice, this defects in graphene has some effect. So, for example, people can use this Raman scattering peak associated with certain vacancy or defects to even identify single layer or bi-layer graphene. So, for example, this Raman peak for different layers of graphenes will have different shape and position. And also, people have artificially added atoms onto graphene. For example, this is one example. They add hydrogen atoms onto graphene, and the hydrogen atom induce a bond state, very sharp impurity bond state. And also, they found this splitting that's due to a local Coulomb interaction of this impurity bond state not very large, but not very small also. And they claim this is a local magnetism. So I mean, this impurity certainly has some effect in typical graphene. And also we know that impurity in superconductors also has an important effect. For example, for non-magnetic impurity in unconventional superconductor will also induce an in-gap bound state similar to this so-called Vishveshwara state for magnetic impurity for S-wave superconductor. So this is from one of the review modern physics paper by Banerjee for the D-wave superconductor. Well, it's a gapless. I mean, it's a nodeless, so it doesn't have a full gap. So this bound state becomes the so-called virtual bound state or resonance. And you can compute it, for example, in real space, the shape of the bound state is quasi-localized. And also for this non-magnetic impurity in unconventional superconductor, you have, in some sense, the so-called violation of this so-called Anderson theorem. Anderson theorem is that for S-wave superconductor, if you have a weak scalar non-magnetic impurity that doesn't seem to affect the gap and the TC much, but if you have non-magnetic impurity in unconventional superconductor, even for weak impurity, that will suppress locally this local gap. And this again from this review of modern physics paper in a D-wave superconductor, you put impurity, non-magnetic impurity locally, it suppresses the gap significantly. So this will principle, if you put a lot of such impurities in unconventional superconductor, it will kill the superconductor. These are all old stuff. So what we did is a very simple calculation, really very simple. So I suppose I can save some time for Subhro for the next talk. So we have to use a model for this twisted bilayer graphene flat Murray band. Unfortunately, there's many models around. We choose this two orbital honeycomb model. So this model site is this AB or BA, AB or BA region. So this AA region, they assume this one orbitals sitting on this AB or BA region, and they have two one orbitals per honeycomb site, and the one orbitals somehow has px and py like symmetry. I actually don't really know a good first principle derivation of this model, but nowadays I think at least two groups, one group in China and this Liang Fu's group use this kind of a model, and this is the band structure is not really that flat, so but the energy scale is very small. The hoppings for this tight binding model is around millielectron volt. And we consider on top of this model, we consider the various unconventional nodeless superconductor. For nodal superconductor, of course, you can easily detect it by other thermodynamics measurements. And there are also some subtleties, so we only consider intraband pairing. So my pairing potential is really intraband, that although the bands are very flat, in principle, this pairing can happen between the bands. Didn't consider that. And for numerical calculation, we put the superconducting gap on the Fermi surface to be around less than 1 millielectron volt. You may think this looks a small number, but think about the fact that this bandwidth is also very small. So this is not a very small gap. And compared to real experiments of 1 Kelvin TC, this is still several times larger, but we are limited by our technical calculation capability, so we cannot do even smaller gaps yet. And this actually, you see, give us some technical difficulty and artifacts. So then the non-trivial thing is, okay, so what kind of impurity we consider? As a first step, we consider very simple impurity. Look, imagine you have one carbon vacancy on one of layers of this bilayer twisted graphene. That's a strong unitary scalar non-magnetic impurity potential. So you have to translate that into this effective tight binding model for Murray band. So we did that, and turns out this suppose in this high energy level you have this short range potential, and then you project that to the Murray band. That's still a very short range potential because this Murray band has very localized one-year orbitals, and the form of the impurity potential in the effective model is rather complicated, but we can fix that by symmetry, by threefold rotation symmetry and time also, etc. And we parameterize the strength of this impurity potential by this dimensionless constant U. And the other parameter dimension for constants here will have the same order of magnitude as this hoppings, corresponding hoppings. This TNN means nearest neighbor hopping, TNN means next nearest neighbor hopping, etc. So in this effective banding model, they are of order of 1 millitron volt. And to calculate the effect of either bound state or the effect on gap, we use a standard, very standard theoretical method. You can pack it up in this review of modern physics. For example, for bound state, we just do this matrix, very simple calculation. And actually, in this calculation, we have to use, in some sense, a finite lattice to do this calculation. And also for this TC gap, Smitha gap, we use this Born approximation. This here actually we have to consider 3 cases: the impurity, the defects, maybe in the AB or BA or AA region, I labeled with 3 different symbols, and somehow for certain symmetry reason, for this second 2-loop picture, the self-energy diagram, this AA impurity doesn't appear. Anyway, so this is the result. It's done by my student. Hopefully. For the S wave, of course, as we expected, nothing happens. So you put impurity, this gap just persists. There's no in-gap state. For the P wave and the D wave, you put on impurity, there's some in-gap state, and you look at this spectrum close to the impurity and far away from impurity, this in-gap peak weight changes, so it really indicates it's localized state. And you may notice that although for the S wave gap, this local density state looks like a simulating gap, the P and the D wave, I have all of these specs. That's really one artifact. I later we realized that because of this technical limitation that we are not using a very small gap, that's really artifact we are hoping to overcome for later work. And also, look at this simulating gap computed for a concentration of such impurities. For S wave gap, this gap size doesn't change much, and for D plus ID and P plus IP, you increase the concentration. Then the concentration and use the strength of this impurity potential, then of course the gap decreases, and actually the P plus IP gap will quickly be surprised and becomes gapless in some sense, gapless simulator, and the D plus ID gap also are quickly surprised by this impurity strength. That's why it doesn't change much. So this is not surprising. So this is finite, in some sense, finite. Not only finite size effect, but also some artifacts I will mention later. So shouldn't be real. Some technical limitation. So fine. So it's a very simple idea, and this result is not surprising. So I probably expected this before doing the calculation. Kind of expected before doing the calculation. Now, can people really do this? So actually, recently people reported scanning tunneling microscope measurement on this twisted bilayer graphene. So they can measure local density states. They can even see this correlation effect split this flat Murray band density state into peaks, and there are some worrisome results. For example, this density state seems to be higher than the AA region than the AB region. Whether this is consistent with all of these previous models with the local linear functions on AB site, I don't know. So worrisome facts. Okay, so what's the time now? Still have a lot of time, I suppose. Okay, so my sentence is my simple story. But the whole take-home message is very simple. So impurity certainly will have important effect for superconductivity, and hopefully in twisted bilayer graphene, if we consider the impurities, naturally existing impurity or artificially added impurities, and we can in principle use it to distinguish different kinds of unconventional superconductivity. So we can in principle measure it in ICTS experiments if we have such a high energy resolution. The gap is already very small, or you can artificially increase impurity concentration in this material by there are many ways. You can put a lot of atom on it, or use, for example, when people use argon bombardment to create a lot of vacancies in graphene and see whether this superconductivity just diminishes quickly with impurity concentration. There's a lot of, as I said, this is in some sense a work in progress, and a lot of caveats and technical problems, limitations for our work. So we choose this two-orbital honeycomb lattice model, which is one of the simplistic model for this twisted bilayer graphene. But certainly it's not the best model that are present here now. So I think Ashwin already made some much more sophisticated 8-band model, but numerically it's much less tractable. And whether we can really quantify the impurity potential from more first principle calculation, that's also a very important question. And as said, there's a technical limitation. We cannot simulate very small simulating gap because of the finite size effect. That actually causes some problem for this P plus IP and D plus idea. I will mention that briefly. And finally, we only considered by so far non-magnetic impurity. So of course, magnetic impurity will kill all semimetals. So we didn't really consider that. But actually, for graphene, there's another interesting topic that for two-dimensional materials, impurity Coulomb potential will not be screened very well. So if you consider Coulomb charged impurity potential in graphene, there's also interesting problems. And whether this Coulomb impurity in this Maury flat band will also cause interesting physics, that I think is also an interesting question to ask. So finally, since I have time, let me mention there's some technical problem. We finally realized why the reason that we are putting, although we think a very small simulating gap, but for the P plus IP and the D plus ID gap, the gap function vanishes at K and K prime, the superlattice Dirac point. And when you open the gap, and although the gap seems to be small, but it's not really that small compared to this K and K primes Fermi energy in some sense, then once you open the gap, the minimal gap is not quite at the original Fermi surface position. So this causes all this artifact, and this causes significant finite size effect. We are still trying to overcome this. Okay, so with that, thank you for your attention.
The speaker finished a good 7 minutes before time plus 5 minutes discussion. So the floor is open.
Main drawback is that it doesn't implement all the symmetries.
True, yeah.
But I wonder, is the symmetry important for your case? Like you said, some diagram was vanishing because of some symmetry. What symmetry was that? You said the
that is so that is this you mentioned this emergent six-fold rotation symmetry in some sense. So this full loop self-energy diagram for this AA set impurity potential is vanishing some due to that symmetry.
I see.
But that is a qualitative result. I mean, don't really depend on this. The unconventional symmetry, so certainly it will be killed by this non-magnetic impurity. How much is a quantitative question, of course, depend on this.
Yeah, so I think the minimal model that keeps all the symmetries is a 5-band.
Okay, yeah, I know.
One advantage of those models is they also keep the nearby bands.
Yeah.
There's no reason the impurity should only mix
that's
flat bands. It will probably mix some of the
as well. I know, but at this moment we're not able to do that calculation.
Right.
So yeah, even in the normal state, just because of the Dirac nature of your low energy states, there will also be bound state near to the impurity that Balatsky and all showed. So, and you will probably get additional one in the superconducting state. So
yeah,
how do you
actually,
distinguish
we also did this calculation for normal state using not this tight binding model, but using this McDonald's effective model. using the T-matrix method, but somehow, surprisingly, we didn't see any impurity bound state from this Murray flat band. We see some bound states from the neighboring bands, typical normal impurity bound state from.
I mean, usually if you have a Dirac point
Yeah.
and you have a very strong onset impurity potential, so you would naturally see a bound state,
Right.
generic model.
So yeah, so I can only say that by so far in our calculation, we somehow in the McDonald's model we didn't see that. I don't know why. Yeah. Okay,
Okay, so then let's try to follow.